My name is Jacob Sealander, and I am the Chief Architect for C4ISR systems with Curtiss-Wright. We're going to talk today about standard interfaces and the benefits of heterogeneous system architectures. So I guess I'm going to cover something that's really obvious to most of the people in this room, since we all live and breathe open standards. But the bottom line is we live and implement and evangelize open standards because it's a great benefit to the warfighter. It's a great benefit to the warfighter because of things like interoperability, things like growing a strong industrial base with all of the people that are here, all the people that are represented on this board, the ability to do tech refresh. And I feel like Mr. Littlefield was a great straight man into what I'm talking about, because the things that are going on in SOSA are going to help these kinds of things, and we'll talk about that a little more. And the better we do in this sort of standards development, the better we can do fast fielding, which is ultimately one of the key things the warfighter is looking for. But the question is, what else can we do? We've talked about these things, we evangelize these things, but what else can we do with open standards implementation? So before I answer that question, I want to focus in on one of the key areas, the key things that are sort of at the backbone of any processing solution is the processing elements. My guess is for the 4 processing elements that are shown here, none of these are a surprise or unknown to folks, but they're all different and they all bring unique capability when you're deciding what am I going to use to provide the computing solution that I want to provide. CPUs in general, easy to implement, based on software, good for a wide variety of things, not very parallel, fairly serialized, threaded, those kinds of things. GPUs, a bit more specialized, highly parallel, good for a lot of different things. But it has to be, a fairly parallelized capability. FPGAs, customizable, can be very low latency solutions, good for things that are consistent and predictive, can be used over and over again, somewhat of a black box. And then ASIC. ASIC is just any one of the things that we just talked about for a very specific use, for a very specific circuit, built hard in silicon and just reused over and over again. All of these things, different benefits, different costs, different barriers to entry, but these are the things that we have available in general. So what does this mean? So as a system integrator, you're trying to, again, solve a problem for the warfighter. I'm trying to say, here's a function or a capability that's needed. How am I going to do this? I've got these different elements. I've got an algorithm I'm trying to develop. How do I do this? The requirements are coming down. I've got all this data to handle. How am I going to move it around? I only have so much available, and someone's talking about, quantum computing, and is that ready? And I wish it was, but I only have what I have. And so how do you do something with what you currently have available that's going to meet today, tomorrow, and quite frankly, the things that we're not even sure that we want to do yet. And this is part of the system integrators issue as they try and figure out, what am I going to do? How am I going to develop these things? So that's a bit of what we're going to chat about today. So enter heterogeneous system architectures. The world at large that is using heterogeneous architectures in cloud computing and all the different areas that you guys are likely familiar with that's using HPC, they use all of these different computing capabilities. They use it for virtualization, for machine learning, AI, all of these things that are buzzwords that we understand. Each of these different computing elements bring value for these different capabilities. So as they all bring value, they all are used in different ways, hence the heterogeneous term. And while that's all interesting and good, there's an inherent issue of the problem, the complexity of selecting these things. How do I know? How do I integrate them? How do I make them play together? But there's this huge industry that's figured that out, or has at least pushed towards figuring that out. And it's really about the standardization of the interfaces. And so something that SOSA is doing, and I'll talk about that a little bit more, but in the end, for all these different computing elements, these elements are being treated like an entity. I don't have to necessarily describe it. I'm standardizing the interfaces that go in and out. If I'm moving big buckets of data, the fat pipes that go in and out, they're network-based. And I can use whatever processing element I want, so long as I standardize on that data plane interface. Same thing with the control system. It's networked as well. They can be very fast. Also low latency things like 1588 PTP that can provide the sort of low latency performance that you need, but again, over the network. Nothing custom, nothing new, nothing specialized. And coherent processing is listed here. That's sort of the data within the system. You get these different elements. This is becoming more and more standardized. There's more things being developed. It's not quite as standardized as sort of the data and control portion, but it's on its way. And this is all about getting those different processing elements to feel like they're all sitting on one chip, and the benefits that you get from having that kind of shared resources. So with all of these things standardized, what this does is gives us the ability in our world to move towards sort of what people have been talking about for, gosh, since my career started, this sort of all-powerful box, a C5ISR EW box, where all these different applications are converging. If you look at sort of the future of architectures, if you try and map out what a mission computer looks like in the future, or what a radar signal processor looks like in the future, or a sensor fusion, or whatever, you start to see those architectures looking more and more and more alike. And that's a good thing, and I think the effort that SOSA is bringing is going to allow that allow heterogeneous computing to really come to life in our space, because we're going to standardize things like what's a computing element, and if I can standardize those interfaces, I don't have to necessarily decide up front what computing element that is, and I'll talk about that a little bit more. So this is just an example of a sort of a heterogeneous architecture, and you can see sort of a standard data in. Here you would see typically maybe a classic architecture, your switch, and then you might see maybe the FPGA was going to be the first receiver of data input and then hand it to the switch and then down to a CPU, and this sort of kind of classic waterfall structure. But as the world moves forward more towards a heterogeneous architecture, CPU, GPU, FPGA, it's not one first and then the other. They're all just elements that are kind of on par with each other. There's not one, slave to another necessarily. They're all viable solutions from a computing situation. And so what you're really trying to do is say, I have a specific application, a specific algorithm that I'm trying to accommodate. Whatever I want to do, I'm still going to have sort of the real world constraints that we have, size, weight, power, those kinds of things that I'm going to have to try and fit inside of. And so now my consideration is really about how much performance can I provide inside of those constraints. But now I have these sort of different elements I can think of as just computing, not have to necessarily say, I know which one it is if I can standardize on those interfaces. So what is the value? Every system's going to have its constraints. How much power it can be, like I said, size, weight, and power. It's going to have its requirements, its goals, and a lot of times there can be a lot of analysis, a little bit of paralysis that goes into how am I going to do this? How am I going to solve this? And of course, whenever we're trying to select what we're using to provide the solution, it's limited by what's available today. We're sort of in love with the thing that's just about to come, but at some point you have to decide to use what you have available now. So while those are kind of the constraints and what it means in our world, if you adopt this standardization of interfaces where I can start leveraging computing solutions as sort of generic components. I can choose technologies for the application that are currently available and within the fixed constraints that I have. What can happen though is if I embrace the fact that I don't necessarily have to pick the exact right computing solution right up front, because I know that I've built in an infrastructure where as I optimize my algorithm, as I figure out where the gotchas are, I can use other elements to pull out and pull in to say I've improved the performance of my algorithm by continuing to develop software that works better, maybe instead of on a CPU, on a GPU, and the next slide will help me explain that better. So if you, instead of saying, I need to develop an architecture and a hardware solution that I'm going to field today and has to stay the same for many years, and the cost of changing it is really, really hard because I got to change the backplane and I got to do software different and all these different things. You build in an infrastructure that says, today with what I have available, I could possibly make a system that does what I need it to do with a 3 CPU system. I generate my algorithm, I test it, it works, and it generates some amount of performance that might be acceptable, and you see as a suggestion, maybe it generates a kilowatt or consumes a kilowatt of power. As time goes on, rather than saying, let me wait to optimize my solution or improve my solution until that next CPU comes out, you can actually say, I found a place in my algorithm to go implement a couple of GPUs. And if those standards have been chosen and have been accepted, you can pull out your CPU element and put in your GPU element, backplace the same. It's consuming the same power, but you're going to get a benefit of capability because you're going to be either using the same level of performance for much less power because you're using a much more efficient computing solution for what it is that you're doing. And then as time goes on, again, instead of saying, I'm still waiting for that next CPU or I'm waiting for the next super great GPU, you find that your algorithm or the computing solution that you really want to use can be a combination of FPGAs and CPUs. And again, those computing elements can be pulled out and put in. And again, the idea is that physically, your swap, you've got the same enclosure, you're consuming the same amount of power, but your performance is going up because of the fact that you're optimizing what it is that you're doing with the right technology at the right time. So application examples might be machine learning. So maybe you'll start with a CPU, GPU, and you'll get sort of whatever you get, but you'll continue to optimize maybe with an FPGA GPU pair, and you don't have to wait to field. You can field a viable solution up front and optimize with the ability to easily retrofit in the background. Electronic warfare, the things that you can do with FPGAs, with the outer loops or sort of the back-end processing with CPUs, there may be things that you can do as you learn about your algorithm where you can maybe drop in a GPU or use a different portion of an FPGA or something like an MP sock that's going to help you, again, increase your performance without having to change at the sort of overall box level the constraints. Mission processing, lots of CPUs for virtualization. This is kind of the trend that we see, but there's going to be opportunities as we adopt more data fusion, analytics, those kinds of things where what you're doing may not just be a string of 6 CPUs together. It might be 4 CPUs and a couple of GPUs, whatever it is, but you're able to optimize your algorithm by the retrofit of the computing element rather than forcing your code down the throat of something that isn't really the best solution for what it is that you're trying to do. So, key takeaways. The open standard interfaces, that if we can do that, which is really what SOSA is about, if we really standardize on these interfaces, we can adopt a methodology of employing different architectures and employ different methods of improving our systems by optimizing the computing elements in the background, using the right element for the right job as the program develops, rather than saying, I've got to make a decision and then I'm going to have to live with it for forever because that's what was available at the time. I think these are pictures from previous presentations from Dave's, but in the end, you can upgrade the computers or the processing elements without upgrading the entire building, which is the chassis of the infrastructure for it. And that is all I have.